Yeah, it's actually, it's not so bad. All right, so look, we've got a spring with a constant of 3.5 newtons per meter, and it's stretched initially to 0.2 meters. All right, so here is where it's stretched out, and it's stretched 0.2 meters from the equilibrium on, right? So this distance that it's stretched is 0.2 meters from the equilibrium. And the spring constant is 3.5 newtons per meter, all right? All right, so the very first thing I have to ask you is how much work have we already done? Anyone know how much work we've already done? How do we figure out the work that we've done? Well, the work was, well, force times distance, but it's too hard to do force times distance with a spring. What we know is that it's stored as energy inside the spring, right? So yeah, I'm going to say that it's the potential energy of the spring because that's where the work got stored. Yes, this is one of those problems that it's easier to look at it through an energy lens, and so that's 1/2 times the K times, I'm going to say A squared because that's where we're at. A squared. Okay, so we've got 1/2 times 3.5 newtons per meter times 0.2 meters, and that's squared. So far, so good. So 0.5 times 3.5 times 0.2 squared. So the total energy in the spring right now is 0.07 joules of energy. So far, so good, right? Okay, the really weird thing about springs and why you don't want to just use force times distance for looking at this is that the more you displace the spring, the more force there is. Springs are variable force. And so it's really hard to look at them from force times distance, right? They're variable force. So then it asks you, well, how much work is required to stretch an additional 0.2 meters? You can't just say, well, it's twice as much because you already know how much for the first one. The problem is the more you stretch it, the more force it takes. That, remember, the force is equal to the spring constant times the distance, okay? And so it's got a variable force. And unless you want to do calculus, this is the hard way to do it. The easy way to do it is say, okay, if I pull it then further out, and now I'm out here, and my new distance is 0.4 meters, you know, how much energy did I store at 0.4 meters? Well, let's see. That's 1/2 times 3.5 newtons per meter times 0.4 squared. All right, 0.4 meters squared. And so that's 0.5 times 3.5 times 0.4 squared. So my new energy is 0.28 joules. And before you say, well, that's the answer, it's not the answer because it asked how much more work to stretch those additional 0.2, right? So that means you've got to take what you had to do to get it to 0.4, right? Minus what you did originally, and the difference between the two is the work that you did between the 2 points. So that would be 0.28 minus 0.07, and what do you get? 0.21 joules. And the reason you can't do that, and you know, when you first look at this, you think, oh, it's easy, twice the force, right? Wait, Mrs. Valletta, there's not 0.14. How is that possible? It takes more, the more you stretch it, the more force it takes. So you can't just do force times distance. It's not a constant force. Are we good? Okay.